Modern roll-on, roll-off ferries are logistical titans. They are built to swallow thousands of tons of cargo, swarms of cars, heavy trucks, and daily commuters, moving them across the ocean with incredible speed and efficiency. To achieve that kind of turnaround time, these ships rely on one defining architectural feature. You are looking at a modern vehicle deck. Notice what is missing. There are no bulkheads, no internal walls. The design is one continuous horizontal space, spanning from one side of the hull completely to the other. But the exact structural choice that allows hundreds of cars to drive straight on and off also creates a severe, almost counterintuitive physical weakness. You don't need a catastrophic hole in the hull to sink one of these massive vessels. All it takes is a breach large enough to let a few inches of seawater spill onto that vast, open deck. That shallow layer of water is all it takes to trigger the free surface effect, a ruthless quirk of fluid dynamics powerful enough to flip tens of thousands of tons of steel completely upside down in a matter of seconds. This diagram shows the baseline physics of how any ship floats. A vessel's stability is a constant vertical tug-of-war. Gravity pulls the mass of the ship straight down through a point called the center of gravity. In response, the water pushes back up against the submerged hull through a point called the center of buoyancy. If a gust of wind or a wave causes the ship to tilt, the shape of the underwater hull changes. The center of buoyancy naturally shifts toward the submerged side. Because the upward push and downward pull are now separated, they create a twisting force, a righting moment, that automatically pushes the ship back upright. Now watch what happens when we apply those same physics to the hollow ro-ro design. We have that massive, unpartitioned floor spanning the width of the ship. If a wave breaches the bow doors, a thin layer of water pools on the deck. When the ship leans even 1 degree, that water instantly rushes across the deck to the lowest possible point. Because there are no internal walls to stop it, the water acts as a massive, dynamic weight. That sudden concentration of mass on the far outer edge forcefully drags the ship's center of gravity horizontally off-center. The shifted weight completely overpowers the buoyancy pushing up from below. The ship loses its natural righting force entirely. Without it, gravity simply pulls the heavy side into the water, resulting in an uncontrollable and fatal roll. This aerial image maps the coastal layout of Zeebrugge, a shallow water port in Belgium. On a cold March evening in 1987, a 132-meter passenger ferry called the Herald of Free Enterprise was loading vehicles here for a routine crossing to England. To compensate for a low tide and align the ship with the loading run-up, the crew pumped heavy water into the forward ballast tanks, forcing the bow to dip. Once loaded, the captain ordered the ship out to sea. However, the assistant bosun had slept through his call, leaving the primary bow doors wide open. The captain, standing on a bridge with no indicator lights, assumed the ship was sealed and departed. As the ferry accelerated past the breakwater, a principle of fluid dynamics took hold. In shallow water, the rapid flow of water under a moving hull creates low pressure. This suction literally pulls the ship deeper toward the seabed, a phenomenon known as the squat effect. The ship was already nose down from the heavy forward ballast, and the squat effect dragged it even lower. As the vessel picked up speed, the mounting bow wave rose rapidly until it breached the open doors, scooping tons of the English Channel straight onto the unpartitioned vehicle deck. The moment the water hit the wide floor, the free surface effect engaged. The ocean sloshed to the port side, yanking the ship's center of gravity violently to the left. The natural righting moment was destroyed instantly, forcing the vessel into a sudden, unrecoverable list. A breakdown in basic communication ended with thousands of tons of steel laying completely on its side. The ship capsized onto a sandbar barely a mile outside the harbor entrance, taking the lives of 193 passengers and crew. This photograph shows the cruise ferry MS Estonia, defined by a massive bow visor that hinged upward to allow cars to drive directly inside. 7 years after the Herald disaster, in September 1994, the Estonia was navigating the Baltic Sea, battling gale-force winds and brutal 4-meter waves. Around 1 a.m., the ocean simply overpowered the engineering. The sheer hydrodynamic force of pitching into the heavy seas ripped the securing bolts right out of the hull. The 50-ton steel visor tore completely off the front of the ship and sank.
Deep inside the ship, the bridge crew was completely blind to the disaster. The angle of the bridge blocked their view of the bow, and the ship's sensor panel, now ripped from its mounting, short-circuited and continued to shine a green light, falsely indicating the hull was perfectly sealed. Feeling the ship begin to lean from the wind, the crew attempted a standard course correction to rebalance the weight. Instead, they unwittingly turned their massive, torn-open bow directly into the oncoming waves. Thousands of tons of freezing seawater poured relentlessly onto the open car deck. The free surface effect took over. As the water rushed to the starboard side, its dynamic weight tore heavy trucks and passenger cars loose from their lashings, compounding the shift in mass and accelerating the list rapidly past 90 degrees. The structural failure in the ensuing physics were so severe that the Estonia fully capsized and vanished from radar in under an hour. Only 138 of the 989 people on board survived the freezing Baltic that night. Two massive vessels lost in completely different circumstances, both undone by the exact same physical mechanism. The Herald and the Estonia proved that the unpartitioned layout of rowrow ferries carried a terrifying fragility, forcing the global maritime industry to completely rewrite its rulebook. Following the Herald of Free Enterprise, regulators realized you cannot engineer away bad communication. They implemented the International Safety Management Code. This legally forced the top executives of shipping companies to implement strict, auditable safety procedures, holding them directly accountable for the daily operations of their crews. To ensure exact operational details are never lost to the deep again, the Estonia disaster drove strict new technological mandates.
Today, all commercial passenger vessels must carry automatic, float-free radio beacons to broadcast emergency locations instantly, as well as voyage data recorders, marine black boxes, to preserve bridge audio and sensor data. Most importantly, naval architects developed rigorous new damage stability requirements. Modern ferry designs now include specialized partial bulkheads and scuppers on vehicle decks, designed specifically to trap and drain intruding water before it can span the entire width of the hull. You cannot change the laws of fluid dynamics. Water will always seek the lowest point, and gravity will always exploit an unbalanced load. But by understanding the ruthless mechanics of the free surface effect, the maritime industry has built the unyielding procedural and engineering walls needed to keep it contained.